Hi, my name is Gunshi Gupta and I'll be presenting work titled Look Ahead Meta-Learning for Continual Learning. This is joint work with my co-authors Karmesh, Yadav and Professor Paull. Continual learning is the problem of learning from a non-stationary stream of data composed of sequential tasks, such that the learned model should perform well on newly learned tasks without degrading performance on the old ones. This is essential to realize intelligent agents that can learn from interaction, for example, home robots and recommender systems. We look at the problem of catastrophic forgetting, which is one of the biggest challenges in this setup. It occurs when a deep neural network undergoes many gradient updates on a temporally correlated stream of data. In such cases, gradient interference between tasks can cause forgetting on old tasks while learning a new one. We ideally want alignment between tasks to make shared progress on them, even when old data is not available anymore. It turns out that gradient-based meta-learning algorithms implicitly incentivize this. This connection was used by MER to show that the meta-learning algorithm Reptile can be used to minimize the loss on a set of tasks seen during continual learning while incentivizing gradient alignment between them. While their objective is meant to be optimized online, it is very slow in practice. The UML objective was proposed as an offline meta-learning algorithm for pre-training a static representation that is later used for continual learning at test time. It uses catastrophic forgetting as the training signal to optimize the representation, which eventually becomes highly sparse, and this helps to mitigate catastrophic interference. Our aim is to develop a fast and scalable algorithm for online continual learning which endows the model with similarly appealing emergent properties such as gradient alignment and sparsity. We therefore adapt the UML objective so that it is optimized online by the model parameters using model-agnostic meta-learning or MAML. A small replay buffer is also populated by reservoir sampling on the data seen during training. We use a MAML update where samples from the new task are used to take multiple inner loop gradient steps and are then interleaved with samples from the replay buffer to compute the meta loss. In this way, we use the OML objective to learn new tasks while maintaining performance on old ones. We validate our algorithm by showing that our surrogate MAML objective is equivalent to a continual learning objective. We call this adapted objective Continual MAML or CMAML, since it proposes a way to integrate the MAML algorithm with continual learning in a fully online fashion. Now, despite the fact that meta-learning can eventually increase the alignment of within-task and across-task gradients, there can still be some interference between the old and new tasks, especially at the start of training a new task. These considerations called for adaptivity in learning to adapt to the optimization landscape as well as speed up learning. However, standard optimizers like Adam are not suitable for this problem. We introduce a set of per-parameter learning rates, or LRs, to be used in the inner loop of the meta updates. We observe that the expression for the gradient of our objective with respect to these learnable LRs reflects the alignment of the inner and outer loop gradients. In our case, these are the new and old tasks gradients. These LRs are thus automatically increased when the alignment between old and new tasks is high, and decreased when alignment is low. We propose updating the weights and LRs in the meta update asynchronously so that we first update the LRs and then use them as the learning rates for the meta weight update. This ensures that the parameter updates we make are conservative with respect to old tasks, since interfering gradient updates are made with lower LRs. We call this modified algorithm Look Ahead MAML or La-MAML. We conduct experiments in the single and multiple pass setups of continual learning that pose different kinds of challenges for a learning system. In the single pass setup, we see each data point only once and can't revisit it later, even while learning the same task. In the multiple pass setup, each task's data becomes sequentially available for offline training until convergence. Our experiments involve learning a sequence of visual classification tasks on the MNIST CFAR100 and TinyImageNet continual learning benchmarks in task-agnostic and task-aware conditions. We define several ablations to capture the gains from the online objective, our LR modulation, and the async update. We see superior performance of our ablations, with La-MAML performing the best amongst them. We also see that La-MAML has a runtime about one-fifth that of MER, a primary meta-learning baseline. In conclusion, we propose a fully online algorithm for continual meta-learning with inbuilt learning rate modulation. It is robust and scalable to bigger problems and performs favorably across different setups and benchmarks. Thank you.